in car following. Here, I will start my presentation now. First, I will give you guys a briefly background about car following idea and anticipation. Then I will introduce the gap anticipation variable we used in research, and then the updating strategy and the model properties. Then I will briefly conclude our research. For car following, which is a very widely spread idea, the main assumption of car following is that the dominant influence of the driving behavior comes from the leading vehicle. Here is some traditional car following models. One is the widely used city model. One is the UL model and the bundles model. Also, there are some other more recently developed models like the Gibbs model, the intelligent driving model, and things like that. They all use the idea that the driving behaviors is influenced by the leading vehicles. The idea of anticipation is usually captured in car following by temporal anticipation or spatial anticipation. For temporal anticipation, people usually consider drivers' estimation of their leaders' accelerations and velocities and consider its effects to influence on the driving behavior. And for spatial anticipation, they are usually considered anticipation spatially by including several leading vehicles. Like an example is the Bottleneck head model developed by Herman, which they consider two leading vehicles. Now I will introduce the gap anticipation variable we used in our model. First, if the following vehicle cannot anticipate the motion of the leading vehicle, then the maximum distance the vehicle can drive is SD0, which is briefly illustrated in this simple graph. Here, the green one is the following vehicle, and the red one is the leading vehicle at time t, and the leading vehicle will move in one time step at the pink one shows the location of leading vehicle at time t+1. When no anticipation is considered, then the maximum distance the following vehicle can drive is SD0, which is the available gap between the two vehicles. When the following vehicle can exactly anticipate the motion of the leading vehicle, then the following vehicle can drive with a maximum distance of SD1. The available gap is longer, but as we can show that if the usual case is that people can anticipate the motion of leading vehicle, but not perfectly. So we introduce the alpha to be the gap anticipation level and waited to get the anticipated available gap SD here. So SD is used as the actual available gap and determine the driving behavior of the following vehicle. Here, as we can see that if alpha is 0, then there is no anticipation as SD is equal to SD0. But if we have perfect anticipation, alpha equals to 1, then SD is strictly is just equal to SD1. Then drivers can have longer available gap and driving faster. Here, based on the definition of alpha, it can be estimated from real traffic data based on the definition. When we set the driver reaction time to be delta t, which we set to be 1 second for the driving reaction time, and based on the speed of the following vehicle, then the distance it can drive is SD, so we can anticipate, we can show the how they drive with reaction time of delta t. Here SD is the available gap and weighted by the anticipation level alpha. Then we can calculate based on this formula to get the anticipation level. Then based on the following speed, the leading vehicle speed, and the time gap and the assumption of reaction time, we can get the anticipation level based on some trajectory data. Here, I show the distribution of the anticipation level. Alpha, by FHWA trajectory data, this alpha distribution is based on trajectories on the fast lane only, because the trajectory data is near a ramp, so we want to eliminate the effects of lane change and tracks. So we only use the leftmost lane data to capture the anticipation level. Here we eliminate alpha data with alpha smaller than 0, because these are conditions where people are doing free driving or acceleration, and they are not doing actually following, so they are leaving more gaps. There are also some values that show alpha can be larger than 1. This may be caused by some overreactions, or some drivers may have smaller reaction time than the average reaction time 1 second. From this distribution, we can see the average is about 0.32, which clearly show anticipation is frequently, and also it seems that it fits a negative exponential distribution. Now I will introduce the updating strategy I used. Is more likely to be a say-like strategy based on the conditions. When the available gap is very small, then the vehicle will do emergency brake. It will stop at the end of the leading vehicle at speed 0. When the available gap is small, but not necessary to do the emergency brake, then the vehicle will drive to the tail of the leading vehicle. if um, if the available gap not is large enough to allow driving without deceleration, then we will apply a probability of random deceleration effect with the probability of random decelerate, and the decelerate is by v decelerate rate is VDEC, which is said to be 1.5 meter per second. If the vehicle is not decelerates, whether randomly or emergency brake or deceleration, then the vehicle will keep on moving. If the gap is allows it to keep the speed but not enough to allow it to keep on acceleration in one time step, then the vehicle will just keep the old speed. And this condition is used to capture some relaxation effect for acceleration. When the vehicle accelerates, there is another indication about the maximum speed. If the vehicle can keep acceleration without reaching the maximum speed, it will keep on acceleration with the given acceleration bt. But if it can accelerate to the maximum speed, then it will only accelerates to the maximum speed and then keep on driving. So the vehicle can never drive with larger speed than the Vmax. Then it's our simulation setting. All the experiments are performed on a 5,000 meter green road with a single lane, and all vehicles are initially stopped with equal gap. The time interval is set to be 1 second, which coincides with the reaction time, and we assume that all the vehicles are identical. The maximum speed of vehicles is said to be 30 meters per second, which is about 67 miles per hour, and vehicle length is said to be 7.5 meters. The acceleration is said to be 3 meters per square second, and the deceleration probability is said to be 0.1, and the random deceleration ratio is said to be 1.5 meters per second. Here I use the time space plot to show how our model can reproduce different traffic conditions. Here the time space plot shows the trajectories of all the vehicles on the ring road, where the horizontal axis represents the location, and the vertical axis represents the time in seconds, and the location in meters. Each white dot is shows the location and the time of a vehicle. So together it shows all the trajectories of every vehicle in the ring road. Here is the time space plot for free flow, but with relatively large density. So most vehicles are free driving, but they have some small disturbance here. The white dots here shows that vehicles have some kind of stop, some little decelerations here. So there are some disturbance here. Then is the second one shows the trajectories for night congestion, where we can see that this small decelerations is more frequently, and this gives you the almost the flow at the capacity. So it shows the maximum capacity with the critical density here. Then it's the pump space plot for heavy congestion, where we can see that drivers experience very frequently stops, or not purely stops, but a lot of decelerations, which will show the pattern of stop and go. Here is the time space plot of traffic jam where the vehicle density is really high, and we can see drivers need to stop very frequently. And here there is a red line to show the trajectory of a specific vehicle. So we can see that they stopped here, and here very frequently. So the traffic is almost jammed. Then we will show how our model can use to simulate some bottleneck effects. The left one is used to simulate a fixed bottleneck, which may be caused by some small accidents or things like that. When the accidents or the bottleneck active at 500 seconds and then last for 200 seconds and then release. All the following vehicles will tie up here and then start to release here. And then they will show a shockwave here and here. The right one shows a moving bottleneck, which that the one vehicle will became a slow-moving track, which reduced its maximum speed to 20 meters per second at times 1,500, and then all other vehicles will follow it to slow the speed. Then we reduce the phenomenon diagram with different anticipation level. Previously, we only show the performance with some median acceleration with some median anticipation level is said to be 0.5. Here we do a comparison between different anticipation levels. First, we will show the fundamental diagrams, which shows the relation between flow and vehicle density relations here. As we assume the anticipation effect to be 0, then we get relatively small maximum flow, which is smaller capacity, which shows that the capacity in this case is about 1,600 vehicles, which is relatively small. We can consider it to be the case that drivers are driving at very bad weather, so they can only see the tail of the leading vehicle. So the overall capacity of the flow is relatively low. Then we will show that the fundamental diagram for median as an anticipation level. From this graph, we can see that the capacity is larger than the no anticipation case, and with the capacity is about 2,200 vehicles per hour. Also, we can see that the transaction between free flow and congestion is more smoother. It's smoother than the low anticipation case, and the congestion range is a little bit wider than the previous one. Also, we show the fundamental diagram for the perfectly anticipation, which shows that for all the drivers, they can anticipate its leading vehicle motion perfectly. Then we can have a very large capacity, which is about it's near 3,000, so it's really high. And also we can see that the transaction between free flow and congestion is much smoother, and also the congestion range here is much wider than the previous one, which with comparing the three fundamental diagrams, we can see that one thing is the anticipation effect can increase the capacity and also can smooth the transaction between free flow and congestion, and also can somehow avoid congestion, avoid the transaction between congestion and total jam, and wider the congestion range. Then our congestion is that the anticipation effect is the main cause of the proton effects. But for proton effects is that there are some vehicles, especially on the HOV lane or fast lanes, there are vehicles moving as a proton with with relatively smaller gaps between them. So they are moving together as a proton. We try to simulate this effect with a variable anticipation level, and we set the anticipation level to be dependent on the gap. For comparison, we set the anticipation level to be 0.5, and then we set the variable anticipation to be 0.9 for very close following, which is the actual gap smaller than 3 meters, and set it to larger when the vehicles are following each other closer, and smaller when they are further apart. Then we use the gap and speed distribution and to show the comparison between no proton effect and the proton effect. We can see here, if there is no proton effect, all the vehicles are restricted by the speed and the gap, and there is no vehicle can drive with a high speed but small gap. While with proton effect, we can have some vehicles driving with small gaps but relatively high speed, and that's what exactly proton effects means. Uh, you have in real traffic. Um, then some conclusions. We introduce the anticipation coefficient alpha to capture the anticipation and look further ahead behavior in highway driving, and designed a CA-like traffic flow model that consider finite vehicle acceleration. Um, Based on the properties of this model, we can show this model can use to simulate different uh, drive, traffic conditions and reasonable phenomenon diagram and bottleneck behavior, and also the proton effect. And the further work we will work on the validation of the model by some real trajectory data, and also think of its applications to some traffic management and control. Then here is the end of my presentation. Any questions or comments?
Thank you so much, Hui. Great presentation. I would like to everyone to, if you have any question, please write in the chat box. There is a chat button that you can click and write your questions there. Hui will then answer your question in a moment. So I'll give you guys a few minutes so you can ask the question. Thanks.
Yeah. What's the question? Yeah, that's a very, very good point. It shows that you mean your question is mainly about the stability of coupling. Here, as is a CA type model, so we do not have so many stability issues here, but also I can see that there are stability problems here. Let me show you on the phenomenon diagram. Here we can see that for the perfect anticipation case, if we have very perfect anticipation, the most ideal case is that vehicles can drive in just like a train. So the phenomenon diagram should have a shape like something straightforward, and then and then there should be no congestion region. But because when the density is high, then the stability cannot be maintained. So the actual flow of the overflow cannot be that high. we can see that if there is a density of 150 vehicle per mile with a maximum speed of free flow speed of 67 miles per hour, we should have a very, very high oil flow, but with chain-like movement, but it's not shown here. It's actually caused by the stability problem. So some kind of stability is already captured here, but not explicitly shown because it's a CA-type model. Is that enough for the explanation about the stability? Yeah, great. Oh, and there is a previous question on slide 5. Oh, you mean the available gap is based on gap at 2 time instance? Yes, that's the case. One is at time t, and one is at time t plus 1. One is for SD0 is for no anticipation, which is the actual gap, and SD1 is the gap in next time step. So they are based on 2. Yeah, that's exactly what is implemented in this model. If you calculate SD1 based on your formula, then it's the gap in next time step. But we want the gap in risk time step to determine the motion of the following vehicle between time t and t plus 1. And you can see the increment of SD0 to SD1 shows the motion is actually V air delta t, which is SD equals to SD0 plus VF delta t. Yeah, actually it's here. If alpha is 1, then we can see that SD0 plus VL delta t. Any other questions?
Okay, thank you so much again, Hui. Thank you all the attendees. I'm gonna copy and paste a link to the chat box. It's a link to the list of the webinars. I will post a link to the PDF slides of Hui and the recorded webinar for future use if you are interested to watch it again or send it to your colleagues. So I would like to express my gratitude to Hui and all the attendees. Our next webinar will be on November 22, I think, with by Professor Papageorgiou from Greece. So I really look forward to that presentation. I will send the email later today or tomorrow about the next webinar. Thank you again, everyone, and see you at next webinar.
Thank you. Bye.